In this video, we are going to look at geostationary satellites. If you recall from the previous video, you will see that we talked about satellites with a height of 850 meters, 850 kilometers, and that satellite was taking 102 minutes to complete 102 minutes to complete one revolution around the sun, around the Earth. Now, as discussed earlier, these satellites, they are not always at the same place if we look from Earth, and so satellites do not provide service to only one part of the Earth. But on the other hand, suppose I want to provide telecommunication services to Australia. Then I want that suppose this is my Australia, then I want that satellite to be here at all the time. I should be able to, when I look up from here, I should be able to see the satellite every second of the day. It should not move away. It should be as if it is stationed here over Australia. It's not moving. When we look from here, we should see the satellite in same position all the time. What it means is that the satellite is rotating with the Earth. So Earth, when Australia is here, the satellite is here. When Australia goes here, the satellite also goes there. When Australia goes there, satellite is still here. So its satellite is over Australia all the time. The purpose of these kind of satellites is that is to provide service to a particular area of the Earth, and normally they are useful in telecommunication. Suppose we have a satellite to provide telecommunication in remote outback in Australia. That means we don't want satellite to go away. We want the satellite to be here. What's the meaning of this thing, that satellite is here all the time? It means the satellite should rotate with the Earth. Earth is rotating on its axis, and Earth takes 24 hours to complete one rotation on its axis. So when Australia is here, it goes back and come here, it will be 24 hours. So this kind of satellite, which is directly above one place and maintains that position with respect to Earth, are known as geostationary satellite. Geostationary means they are stationary with respect to geo, which is Earth. So stationary with respect to Earth. And obviously you can see that when Earth completes one rotation on its axis in 24 hours, the satellite should also go and come back at the same position. So geostationary satellite means that Earth let me write like this. Satellite should take same time to go around the Earth as the Earth takes to complete one rotation on its axis, which means that the satellite's time period T should be equal to 24 hours. So the Earth takes 24 hours to complete one rotation, and the satellite would also take 24 hours to come back to the same position. So if we have that kind of situation, then the satellite would be stationary as looked from the Earth. If I have one satellite stationed above Australia, it will always be above Australia. So what we are going to do is we are going to find the orbital radius, or rather we are going to find the height of such a geostationary satellite. Objective is to height of a geostationary satellite. So what we have here about the situation, I'll draw the diagram here for ready reference. So that's my Earth, and that's my satellite. this would be h, and that would be the radius of the Earth. Mass of the Earth is 5.97 times 10 to the power 24 kilograms. So again, I'm going to use the relationship between t and r. So t square is equals to 4 pi square gmr cube. But this time we are finding r, so I'll write it other way around. I'll rearrange it, and I will get gm over 4 pi square and t square. So we'll find the r, and r is the distance from center to here. That's my r. This is what I'm trying to find. Once I find this, I will take away re to find the height. So the quantities here, m is 5.97 times 10 to the power 24 kilograms. G we already know, and t is equals to 24 hours. But in physics, we only use time in seconds in formulas. So 24 times 3600, sorry, not 34, 24 times 3600 seconds, which gives you 86400 seconds. That's what we're going to use in our calculation. So let's plug in the values here. R cube is equals to 6.67 times 10 to the power minus 11. That's my m. This is my 4 pi square, and I can write my t square here. So 86400 square. We solve this, plug in the calculator, and we get 7.5295 times 10 to the power 22. That's r cube. So raising both sides to power 1/3, we get, or taking cube root on both the sides, I get a orbital radius of 6.3. Sorry, a mistake. So if I do this, I will get a value of 4222691.18 meters. So to find height, I take away radius of the Earth from this. So h is equals to 4222691.18 minus 6.371 times 10 to the power 6, which gives me 358.55910.18 meters. Divide by 1000, I get h in kilometers. So I get 35855.91 kilometers. So this is the height of a geostationary satellite above Earth. It is approximately, you could say approximately about 36,000 k's, or you could say 35,900 kilometers. So our geostationary satellite, all of them are stationed at at this height above Earth, and this is very far. In fact, this is very far. So everything, like when these satellites try to send signals to Earth, they need to transmit them at a much higher power, and the same is the case with us. When we are sending signal back to these satellites, we need to send the signals at a higher strength with higher power. Only usefulness of these is that these are stationed at one particular place, so they provide continuous and constant service to a particular region on the surface of Earth.